Okay, many of you were here on Sunday, and actually, I was quite happy that Abhishek took the time to do the recording. He's not here. Give him a hand. I'll tell him that you all gave him a hand. I mean, it was on a weekday. I mean, it's a Sunday. You guys had a vested interest in being here, but out of the good of his heart, he came and did the recording. So it was good of him. And so is the recording all online? Have any of you seen it? so you assumed it is online. Okay. So what I want to do today is actually complete chapter 12. So Alenka covered the rest of the programming side of parallel processing, as well as the operating system support that is needed in order to. So the three things that I wanted you to get, because parallelism is so important in modern processors, right? Because every processor is a dual core, multi-core, and so on and so forth. And so understanding what is going on inside the box, it's so important to know how to exploit parallelism, right? And that's the reason that we're studying this particular unit. And we learned how to do parallel programming when you have multiple threads, how to synchronize among the threads, and then how to share among the threads. And sharing becomes very easy because it's a single process, so the memory space shared by all the threads is the same, and therefore sharing comes for free. But there's also the problem, right? Because when sharing comes for free and all these threads can execute concurrently, then they can clobber each other. And that's the reason that you need the synchronization. And you looked at mutual exclusion lock as one way of doing the synchronization so that you can get an exclusive lock. Basically, what happens when you get a mutual exclusion lock for all the threads that are executing? What happens? When let's say multiple threads are there and they all are trying to get a lock, one of them gets the lock. What exactly happens at that point? Pardon me? First thread to get to the lock gets a lock, and then what happens? If they want the lock, they have to wait, right? So it doesn't mean that it shuts out concurrency, right? So all of them are executing concurrently. One of them says, I want to mess with some shared data structure. I want to get a lock. Okay, when that particular thread tries to get the lock and gets the lock, then it doesn't mean that the other threads are shut out. They're continuing execution. The only time they'll get shut out is if they also compete for the same lock, right? If they compete for the same lock, then naturally they have to be sequenced in time, right? So the whole point of and the reason why you're having this mutual exclusion lock is to ensure that that the appearance of changes that are made to a shared data structure is sequential, right? Because you cannot have concurrent modifications of the same data at the same time, right? So you want to sequence it somehow, and mutual exclusion lock is the mechanism by which you do that. Is that idea clear, right? So so I want you to get this in your mind clearly that it doesn't, just because you have a lock and a thread is acquiring the lock doesn't mean everybody is shut out. Everybody can continue to execute so long as they don't compete for the same lock at the same time, right? If they compete for the same lock at different times, that's also okay, right? So somebody gets to a lock first, gets it, and then releases it. Somebody else comes to that lock later. There's no good contention among them. It's only when two threads simultaneously or multiple threads simultaneously come to their code execution. And that can happen, right? You have no way of predicting the relative order in which these threads are going to execute. And so in time, if they come to the same point in the code, in the respective code, where they're trying to access the same lock, if it is different lock, again it is different, right? If they're trying to acquire the same lock, then they have to get sequenced. That's the key point I want you to get, right? And once you understand that concept, then this is very important because you're going to be writing the next project that you're starting to work on is thread programming, right? And one of the common errors that happen in thread programming is that you acquire a lock and forget to release it, right? Because these are two independent operations. You get a lock and do something with it, and then you release it. But you forget to release it, then there's a synchronization bug, right? So these are the hard problems that come about in parallel programming, and that's what you have to be watchful for when you're writing parallel programming. So that's the programming part of it. So we understood how to do that, and we also introduced the notion of condition variable. So what is the purpose of condition variable? Yeah. Right. Right. So the point is, why do we need condition? Suppose we have mutual exclusion lock. Why is that not enough for what you want to do in parallel? What is it that the condition variable gives you that the mutual exclusion lock doesn't give you? Yeah. And when you say condition, what exactly is that? What is the condition? So you can, so in other words, when we talk about mutual exclusion lock, that is a service provided by the operating system, right? And the operating system has no idea what you're doing in your program, and all it is saying is it is giving you a facility by which you can say, well, if multiple people come to the same point at the same time, sequence them. That's what mutual exclusion is doing for the programmer. But the operating system has no idea of the semantics of sharing that is going on. I mean, your lock, you have a particular lock to access a variable. The operating system has no idea what variable you're going to access because of acquiring the lock, right? And so that is the level at which the operating system is working. And now condition variable is a vehicle by which you can say, I have a condition in my program. By condition, it's some predicate that you're testing. You want to say A equals B. That's a predicate that you're testing, right? Or you want to wait for some variable to change its value. That's a condition you're waiting, and when you wait, and that condition for it to occur is something that is entirely orchestrated by your program. The operating system has got nothing to do with it, right? Now, there are one or two ways of accomplishing that, and one way is to do what is called busy waiting, right? So, what is busy waiting? Nick? Pardon me? Yeah, so suppose let's say that Nick is going to set a variable to 1, and I want to know when Nick is going to set it to 1. So I'm an independent thread. I can keep polling that variable, right? Continuously looping, waiting for that variable to change value. Eventually Nick will come back from lunch and set that variable to 1, and then I'll be ready to run again, right? And that's one way of accomplishing this. So you don't have to add anything more to it, and you don't even need mutual exclusion. You shouldn't have mutual exclusion for that, right? If I want to do something like that, I shouldn't have mutual exclusion, because I want to be checking this value, and I'm checking a value, and therefore it is okay if I keep checking an old value. But when he comes and changes it, I want to be able to see that change so that I can react to it and then go on with what I have to do. So that kind of synchronization is called busy waiting, right, or spin lock. And the downside, what is the downside, Nick, of doing inefficient, because it is wasting processor cycles, trying to, I'm continuously spinning for a condition that's not going to change until Nick comes back from lunch, okay, maybe a long time. And that's the reason why it is inefficient. And therefore, if you have other things to do, you might as well give the processor up for that, right? And that's the purpose of the condition variable, right? The condition variable says that, look, I'm waiting for x becoming 1. Until that happens, block me. Okay, I'm going to wait on a condition variable. And again, the fact that you have a variable called x in your program, does the operating system know? It doesn't know that, right? All that the operating system is saying is, you say you want to wait on a condition, okay, I'll put you to sleep on a condition variable. And when will I wake up, Taylor? Yeah? Condition variable has been signaled, right? So and who's going to do that? Nick. Yeah, so Nick is going to come at some point, set the variable x to 1, and he doesn't know I'm waiting for it, but he says that if somebody is waiting on this condition variable, then I'm going to go ahead and signal it, because that guy could be waiting forever otherwise, right? And so again, the association between x, the variable that I'm waiting for it to change, and the condition variable I'm waiting on, that association is in my mind as a programmer, right? And in Nick's mind as a programmer, because we colluded together on writing this program, but the operating system has no idea, right? The operating system is just providing a facility, just like mutual exclusion. It is providing a facility by which you can say, when I want to wait on a condition, I can do a wait, and that means I want to go to sleep, and I'm not using the processor resource, and along comes another process, another thread, and it says I want to signal. So wait and signal are the two mechanisms that the operating system provides you in order to do this rendezvous between independent threads of execution. So the first thing that we talked about, mutual exclusion, is not rendezvous, right? It is to get exclusive access for modifying some data structure, right? And in fact, as I said, if the timing is such that you never compete for the same shared data structure at the same time, you don't need mutual exclusion. But because of the fact that you have no way of predicting the relative speeds of the threads, you have mutual exclusion to make sure that when you're making changes to a variable, nobody else is changing the same variable at the same time. So that's the idea of mutual exclusion. On the other hand, the condition variable is there specifically to provide rendezvous mechanism, right, between threads, that I want to do something, but I cannot proceed any further until I know Nick has also come back from lunch, right? And therefore I'm going to wait at that point. And when I wait at that point, I get the signal, and then I can go on. Sure. Right. So Shoaib's question is, if there is a condition variable C, right, and then let's say there's T1 and there's T2 and there's T3, and so this guy says wait on C, okay, and this guy goes on for some time, and then he's also saying wait on C, and this guy goes on, and at some point he's going to do a signal, right? Now, so at this point, what happens is the operating system puts T1 on this queue. Okay, so this is the queue of the operating system for condition variable C. So it's going to put T1 on this, and then so this guy is blocked, right? This guy is blocked, and then along comes T2, and we're going to put T2 on the same condition variable, right? And so both of these guys are waiting, and at this point there's a signal. What's going to happen? So what the operating system is going to do is it's going to look at that queue, and it is going to wake up T1. Now this is where the semantics comes in of the operating system. You as a programmer, you cannot make any assumption about the order in which the operating system is going to wake up T1 or T2, or even whether only one of them will be woken up. You have no way of making that assumption. Okay. So what you have to assume is, you may, when a signal comes, it is possible that some implementation may wake up all the threads that are waiting on this condition. Okay, there is something called, in pthread, there is a way of doing a condition broadcast. There is a condition signal, and there is a condition broadcast. Condition broadcast says wake up everybody that is waiting on a condition variable, and condition signal is saying that wake up exactly one thread that is waiting on a condition. Okay, and so given that, it is possible that both these guys will get woken up at the same time. Maybe one of them will get woken up when this condition signal happens. Now the most important point is, you started waiting here, right, because some variable that you were monitoring was 0, right? That's the reason. Some predicate that you're testing was not satisfied, and you say that, well, I have to wait, right? And so the point is that when the signal comes here and you want to restart, the first thing that you want to do is assert that this signal has been changed. I mean, this condition has been satisfied, right? because it is possible that both these guys woke up at the same time, right? If the operating system woke both these guys up, it is possible that both of them woke up, and when they woke up, one of them is going to be able to see that this value has changed, and then it is going to assume certain state of the program and go on, and therefore you want to make sure that this predicate has been is satisfied before you continue with the execution. If it is not satisfied, then you go back to sleeping again, right? So is that idea clear? Does it answer your question? Okay. So this is something that the operating system is doing, is implementing these semantics in the runtime of the operating system. Okay. So that's the programming side of it. Any questions on it? Okay. Then the operating system side of doing this is providing a library that implements these semantics, right? And so we talked about several ways in which the thread library may provide those semantics. What goes into the operating system in terms of waking up threads, that are waiting for the same. First of all, in terms of structuring the thread scheduling, that can be done in several ways. One is you can make the operating system completely agnostic to threads, right? Meaning it doesn't know anything about threads. The operating system only schedules processes, and what you're doing is all these mechanisms like mutex lock and condition variables are things that you implement as part of your application. That's what is called a thread library, right? If you take an advanced operating systems class from me, the very first thing that I'll make you do is write a thread library, okay? So that's the idea behind providing the facilities for threads to coexist in an application entirely at the user level. That's called user level threads, okay? And that means that even if the operating system doesn't know anything about threads, you can actually have a threaded program run on top of the operating system. But modern operating systems are all thread-based operating systems, whether it is Microsoft Vista or whether it is Linux, they all support multiple threads. And so with multiple threads, then all the semantics that I mentioned in terms of mutual exclusion law, condition variables, they're all implemented by the operating system. And what the operating system is doing is it is actually scheduling individual threads, not entire process, but individual threads of a process. So if you have a process with multiple threads, then each one of those threads gets its time on the processor. Okay, and so those are the variants that we looked at. And as one concrete example, we also looked at the Solaris operating system, right? Right? So no? Yes? No? Maybe? Well, okay. In that case, I'll just show you. So this is, Sun Microsystems operating system has this Solaris is the name of the operating system, and the way it implements thread is as shown here. And so this is the user land right up to this point, and you may have a process that is single threaded. This is a normal process, a single threaded process, or you can have a process that is multi-threaded. Okay, and this is also a multi-threaded process. And so in the structure of the operating system, the Solaris operating system, there are 3 levels of threads. Okay, there is something called kernel threads. Okay, and these are the entities that the operating system is scheduling on the processor. So if there are multiple processors, then it is going to schedule each one of these on a different processor. Okay, these are what are called kernel threads. These are the entities that the operating system is managing to schedule processes, and above this is what is called lightweight processes. Okay, and let's start top down first. Okay, so let's say that I click an icon and I start up a program. Okay, then what you're doing at that point is you're creating what is called a user level thread. So this is what you see here is the user level thread, right? And what the operating system is going to do is, for every user level thread that you create, it is going to associate what is called a lightweight process, which is in the kernel, right? it is associating this lightweight process and so there is a one-to-one association between the user level thread and the lightweight process. But this is not the one that the operating system is actually scheduling on the processor. So it has this entity which is called kernel thread, and so it makes this lightweight process a one-to-one mapping to this kernel thread. So these things, what you see at the bottom, exist forever. So when you boot up the operating system, there's a whole bunch of kernel threads existing, right? And these lightweight processes come into existence every time you create a new process. So when I created a new process, it created this lightweight process and it associated it with this kernel thread. And once the association is made, now every time the operating system schedules this particular kernel thread, it is actually scheduling this lightweight process, and by association it is scheduling this user level thread. Is that idea clear? Okay, so that's the way a normal uni-threaded or single-threaded process is going to execute on the Solaris operating system. Yeah, Ron? Right. Yes, so you can imagine that the kernel creates a whole pool of threads. Maybe it starts up 64 threads, depending on the number of processes it has. Pardon me? Not just the cores. It is even if it is a single core, it will create a whole bunch of threads, because you remember that even if it's a uniprocessor, your operating system is it's supporting multiple threads at the same time, multiple processes at the same time, right? And so it's going to create a whole bunch of kernel threads, and so these kernel threads, once it is created, then at the time that you instantiate a user level program, then it is creating this lightweight process, and then it is creating this association between these guys. Okay, and now you might wonder why, first of all, it creates this lightweight process, right? And the reason is because first of all, let's back up a little bit and say, okay, in this picture I'm showing you a user level process, user level process, user level process, and these kernel threads, this one, this one, this one, this one, and this one, they're all associated with user level processes. But there's a whole bunch of other threads that are sitting here that are not associated with anything. What are they doing there? What is the purpose of those threads? Any idea? Kernel operations. So what do you mean by that? Right. So for instance, I talked about paging daemon, right? So things like paging daemon, network service. When a network packet comes in, so somebody's got to look at those network packets. All those are run as daemon threads by the kernel. So these are not associated with any user process yet, but the result of getting a network packet may be something that has to be passed up to a user process. But when a network packet comes in, the operating system has no way of knowing at that point who it is intended for until it starts analyzing the packet, right? And so these unattached kernel threads are the ones that are doing the chores of the operating system in the background. Okay, exactly what Taylor said. And so when you create a process, it is actually making this association. And you can see that the state that is associated with this guy, which is a daemon thread, is very small, right? It is kernel state, nothing to do with user state. But on the other hand, the state that is associated with this guy is equivalent to what you think of as the PCB, right? The process context block, because that is the entity that says, does this process have network sockets open? Does it have files open? All those sorts of things. And that's the reason that you have this entity called lightweight process that is created at the time that a user spawns a new program. Is that idea clear? Okay. So this is a way of managing the information that the operating system has to keep for different things that is going on. So in the case of things that are happening in the kernel, the daemon processes, the operating system doesn't have to maintain any state other than what that particular thread is doing at that point of time. It doesn't have to do anything to do with user level state, like priority and things like that. And that's the reason that the data structure that will be associated in the kernel for these kernel threads is very small, right? On the other hand, the data structure that is associated with LWP is going to be bigger, right? It is like a process context block, okay? And so this is the way you're creating a new thread of execution. And now let's look at what is going on in this circle here. So here, this is not a single threaded process, but it is multiple threads, right? And now, if you have the pthread library, for instance, what you would do is, from your main program, when you do a pthread create, at that point you're spawning a new process, new thread within that same process. And so this may be the starting point, your main program, and you did a pthread create foo, and at that point you created a new thread. And you notice that when you create a new thread, what the operating system does is it associates a new LWP with this thread. Okay, and so now we got two threads of execution, so two concurrent executions, and you can see that this extends all the way down to the kernel thread. Or in other words, if I have multiple processes here, then thread T1 can run concurrently with thread T2. Okay, and now that brings up the question of why is it that we have these springs that I've shown inside the kernel. Now these are what are called user level threads. So what you're doing when you do a pthread create is you're creating a user level thread. Okay, and when you create a user level thread, you have the option of saying, do you want this user level thread to have a concurrent execution with the parent thread, or do you want it to work in coroutine mode? Do you understand what I mean by coroutine? Sherb says yes. What is coroutine? On what? So in other words, suppose I say that, look, I don't want this new thread I'm creating to have an independent existence, but I want it to share the resources with me. Okay, the processing resource with me. That's what is called a coroutine model. It is either T1 is going to run or T2 is going to run. It is never the case that T1 and T2 are going to run at the same time concurrently on the processor. Okay, if that is a decision that you want to take in your program, then the operating system gives you the ability to say that when you create T2, you say that I'm creating a new thread, but by the way, don't make it a separate existence. Let it share the LWP with me, and therefore you see now T1 and T2 are bound to the same LWP, lightweight process. In other words, if you look at it all the way down, either T1 is going to run on the processor or T2 is going to run on the processor, but never the case that both of them will be running simultaneously on two different processes. Is that clear, Taylor? Oh, so it'll actually tell you very nicely. It'll tell you that no, you cannot do a thread create. Okay, so it is going to have a fine. I mean, this is true even if even in an operating system that does not support threads. One thing that you can try is write a program which continuously forks processes. Right? At some point, the operating system is going to say, no, I cannot fork any more processes, because every user is allowed certain number of processes that you can create at any point of time. So it has a system limit for an individual user, and there is a system limit for the total number of processes or threads that it can create. So when you try to exceed that, it is going to say no. I mean, all of these are limits. I mean, when we talk about file system, it is the same thing, right? So if you create a file, in principle, you can keep on creating as many files as you want. But if you run out of space on the disk, the operating system is going to tell you, right? So when you hit the physical limits, you're going to know in a very bad way. Alazar? Advantage of? Oh, this kind of user. So first of all, let me make sure that you all understand. So the reason why in Solaris there are 3 levels of threads. There is a kernel thread, there is an LWP, and there are user threads, right? And the reason is the kernel thread can be associated with the user level process, or it can be completely unattached, and that's the reason that you have that. And LWP you have is because this is a way by which you can give a processing resource to a user level entity, right? And that's the information that you have to gather and keep about a particular process is all contained in this LWP. Okay, and then the user level thread is the mechanism by which ultimately, when you as a program you create threads, you are creating user level threads. And now Alazar's question are those 3 levels of threading in Solaris understandable? Okay, the need for it. Now Al-Azhar is not convinced of the need for user level threads, right? So in particular, Al-Azhar is asking, what is the reason, what advantage do you get by creating user level threads, but they don't have independent existence? Any idea why that might be a good idea, Taylor? Well, not necessarily. It's not necessarily true. So in fact, what the operating system knows about is only LWP. Right? It doesn't, it doesn't know. It knows that these guys are on the same LWP, and when it is scheduling, it is only scheduling LWP at a time, and so the amount of time that it is giving is commensurate with that LWP. And so, for instance, let's say T1 is the one that is currently running, and it makes a blocking call. Let's say it makes a blocking call. What's going to happen? Both T1 and T2 are shut out, right? Because the operating system knows that LWP has made a blocking call. It doesn't know whether T1 made it or T2 made it, but it's just going to block it, right? And now so in that sense, you're not getting double time on the processor, right? But what you're getting is T1 and T2. You as a user program, you've decided that T1 and T2, I've functionally made them separate threads, but it is never the case that I can have useful work done by both of them running at the same time. Okay, so I know that if T1 is running, T2 cannot run. That's a decision that I made in the way I've structured my program, and therefore I'm just saying that let's not waste the processor resource for that. And that also means that if T1 and T2 are doing some things that are mutually exclusive, you don't have to worry about synchronization among them, right? Because they're never going to mess up with a data structure at the same time, because by definition you said that T1 is going to run or T2 is going to run, not both at the same time. And all the things that we talked about, synchronization, mutual exclusion, is because of the fact that potentially they may hit a point where they mess with some shared data structure at the same time, and therefore I need mutual exclusion. But now I'm eliminating that mutual exclusion by saying that T1 and T2 are never going to run at the same time. Is that idea clear? Okay. Meba? Right. So if I did not have LWP, right, then T1 has to be bound to the kernel thread, and T2 has to be bound to another kernel thread also, right? And then all the binding you're doing at this level, okay? So Maba is saying, get rid of this guy and let's bind it directly to the kernel thread. Now the problem is, as I said earlier, that the data structure that is maintained for the kernel thread is very minimal if it is unattached to anything, right? But if it is attached to something, then the data structure is much more. So in fact, your question is actually, why we need LWP in the first place. That's really your question. And the reason you need LWP is because the state that is associated with the user level activity is much more than the state that is associated with the kernel level activity, right? And that's the reason that you have this. And that also brings up a very good point, and that is, if you think about context switching, right? Context switching, we have said that it always takes time, right? Going from one, going from one thread to another thread, it's going to take some time. Okay, and now if you look at it at the lowest level, if I'm going from let's say, let's look at each of these things. All of these, anytime there's a context switch, what we're doing is at the lowest level we are switching from one kernel thread to another kernel thread. That's what we're doing, right? So whether it is a context switch from here to here, or here to here, or here to here, or here to here, all of these means that I'm going from one kernel thread to another kernel thread. Are all the costs going to be the same? Is the cost going to be the same in terms of context switch? Michael nodded your head saying no. Nodded your head. No, you said no. Why did you say no? But intuitively you think it's not going to be the same. Shane? This one? Well, so actually, what I want you to tell me is, let's say that I'm running, let's say I'm running this. Let's assume that there is a single processor, okay, not multiple processors, single processor, and I'm running this kernel thread, okay, and if I want to switch from here to here, there's another kernel activity that I want to do, okay, that is one level of switching that I can do, right? And another switching that I can do is, let's say I'm running this thread, okay, and this guy is going to hand off to T2, okay, meaning that there is no the kernel is not changing anything, right? Actually, let's start with that. Let's start with this guy. So let's say that T1 is currently running, and T1 says at some point, I'm going to yield the processor. Okay, because remember that it is running in coroutine mode, which means that it is actually not going to block any time, but it's going to yield the processor to somebody else. So it says, I want to yield the processor. Okay, when it says it wants to yield the processor, then T2 can run on that, right? That's also a context switch, right? You're context switching from T1 to T2. Now the good news is you're not changing anything with the kernel thread. So in other words, the process, all that you might have to do is, the processor registers that is contained in the TCB, you may have to load it, but beyond that there is nothing more you have to do, right? Is that idea clear? So that is one kind of context switch that you can do, which is at the level of user level program. Okay, so I'll write that down. So there is user context switch. Okay, and the second level of context switch that I can do is I'm in this program, and then I decide that remember that there is a single processor, right? And the time quantum is up for this guy, and so the operating system is going to switch to this thread. Okay, so it is going from this LWP to this LWP. So that is LWP to LWP in same process. That's the second level of switching. Okay, a third level of switching is the operating system decides that the time quantum is up for this guy also. Now it wants to schedule this guy, which is a different LWP in a different process, right? So this is LWP to LWP in different process. Okay, and then the last thing is kernel to kernel switch. Okay, so let's say that these are all the different ways you can think about context switching. So if you start with this, if it is switching from a kernel thread to a kernel thread, then it is the same address space, right? It's all in the kernel address space, and so the only thing that you have to do is change the register values or something, and then you're done. So you can start executing. So this will be this is one level of switching. Now take the user context switch. So among all these things, what do you think is going to be the least expensive? So I said 4 different ways of thinking about context switches, right? Which is the least expensive, you think, Charles? User. Why is that? So in the case of user, I'm not even changing the thread, right? It's the same thread. It is just that some registers, they may have to be changed in order to run T1 or T2. So that level of context switch is going to be the cheapest. Is that idea clear? No? It's not clear to you. Why? But it is actually changing the there is a TCB associated with, there's a kernel context block, right, associated with this thread, and there is another so let's look at this one and this one, right? This is what we're talking about is kernel to kernel switch. Okay, there is a data structure associated with this guy, and that has to be saved, and then you have to go to this. So there's a little bit more work. Maybe you're right that the amount of work that is involved is not tremendously bigger than this user level switch, but still it is more work because of the fact that you are changing that kernel association, the kernel thread association, right? So the cheapest is going to be this guy, and next is going to be this guy, and what about these two? So the LWP to LWP within the same process is going to be more expensive than either this or this, but it is going to be less expensive than switching from LWP to LWP in a different process. Why is that? Yeah. Right, and also remember that when we are when we are going from here to here, what is changing is the thread control block that is associated with this LWP, but the context for the user process is much more than that, right? What is all involved in that, in the user process? The address space, right? The memory address space and the page tables, all those heavyweight entities are associated with this P1, and that doesn't change going from here to here, right? Because it's the same page table. So all those things are the same. And even the memory contents, the memory hierarchy, now we know there are several levels in the memory hierarchy. There's L1 cache, L2 cache, and so on and so forth. Now all of those are still warm, right? All of those are still warm because we've been running this process. It is just that a particular thread of that process was running, but it was running this process, and therefore all the levels of the memory hierarchy are warm with data that belongs to this particular process. And therefore when I switch from here to here, yes, it is expensive, more expensive than going from here to here, but the user level state is all there, right? And therefore that switch is going to be less expensive than going from one process to a completely different process. Then you're completely changing the page table, you're changing the the locality of the program because it is a completely different memory footprint, and that is going to result in a lot more expense. So when we talk about expense, we are talking about direct expense. When when Shane said, well, kernel to kernel thread may not be also that expensive. You're right, but it is actually accessing a different code path probably, right? So the implicit cost of doing that switching is much more because you're affecting the memory footprint of your traversal in your program, right? And on the other hand, when you go from here to here, you are in the same user process, and therefore the footprint is going to be hopefully shared by all these threads within the same process. When you're going across, it's even worse. Okay, so that's something that I want you to understand in the way the operating systems are structured. Okay, so let's take a short break, and then I'll talk about hardware support for parallel programming, and then we'll do a PRS. Okay. Hey, Baba, I give you your test back. I gave you the points. Right? Yeah, that'll be fine. Yeah. Okay. Hi, Kirak. Is it okay? Is it okay? Not right now. I have a meeting, a faculty meeting at 11, so I have to run for that. In fact, I want to finish this 5 minutes early so that I can run to that. But I'm. 1 o'clock is fine. Yeah. Good afternoon. Yeah. I saw that. Yeah. Okay. Yeah. I'll come look for you. When I'm free, I'll come look for you. Pardon me? so I want to spend another 10-15 minutes talking about hardware support for threads. I didn't expect to spend so much time on operating system support. So, pardon me? Oh, is that right? Okay, so it was good. Okay. Okay. All right. So, so now I want to talk about hardware support. I mean, so particularly, you know, what you have is we are talking about mutual exclusion lock and so on and so forth. So, you know, but we know the reason why we want to get mutual exclusion lock is because we know that instructions are atomic, right? In the processor design, we know instructions are atomic, but what we want is atomicity for a group of instructions. That's the reason that you have mutual exclusion lock, right? But you have to implement the mutual exclusion lock, and all you have is memory, right? All you have is memory to implement locking, and so, you know, if I have let's say, you know, memory over here, and there are two threads, T1 and T2. They want to get a lock. Lock itself, getting a lock is itself going to take multiple instructions, and we'll see why that is so. Because think about what a lock is. So lock is, let's say, a memory location, and I'm going to call this a binary lock. Okay, and the semantics is that I'm going to have a value of 0 or 1 for this lock memory value. Okay, and if I want to get a lock, I want to say if I set, see, let's say call this L. So if L is equal to 1, then I've locked it, and L is equal to 0, I've unlocked it. Right. So let's say that this is the semantics that I want for this memory location. If I want the semantics, then if a thread wants to get this lock, set this lock, first it has to know that nobody else has got it, right? So how will it know? Well, it has to go and check that location and see whether that value is 0. Okay? If that value is 0, then it knows that nobody else has got it. Then it wants to set it to 1 to indicate that I've got the lock now. Is that idea clear? So you want to first test it, that memory location, and see if currently nobody has it. If nobody has it, then you set it to 1 to indicate that I've got it. Now once you set it to 1, if somebody else comes along and looks for that same lock, you know, they'll find that is already a 1, and therefore they cannot get it, right? So this ensures mutual exclusion. Is that idea clear? Okay. So this is what is called test and set. So you're testing a memory location and setting it, right? And this has to be done atomically, right? Has to be done atomically in order to make sure that nobody else, you know, otherwise you have a race condition, right? When multiple entities are going to do that. Shane? Pardon me? Yeah. So we're going to see that in a minute. So now you understand what I want, right? So the semantics I want for this particular thing is what I call test and set. And this test and set says if L is equal to 0, then set L is equal to 1. So this is what I want as the semantics of this instruction. And I want to do it atomically, right? Given LC 2200 instruction set, can I do that? Yes? No? How many think yes? How many think no? Okay, sure. Why do you think no? Well, so no, but think of implementing this in LC 2200. What, you know, given LC 2200, the way you would do that, how would you do it? Load the value, right? So there's a load instruction, gets it into a register. Okay, then you can check if that value is 0. Second instruction. Third instruction is store 1 into that memory location. You need 3 instructions minimum, right? Minimum 3 instructions in LC 2200 in order to implement this. And each of those instructions is atomic, but the 3 together they are not atomic, right? And that's exactly the problem Shane is saying, right? So there are multiple. If thread T1 is running on one core, T2 is running on another core, and both of them are trying to do this test and set at the same time, those 3 instructions can interleave like this, right? and both of them can think that they got the lock. Is that idea clear? Okay. So you need a new instruction. So we enhance our LC2200 with a new instruction which is called test and set, which has the semantic that, you know, now you're a hardware designer, so you can actually make sure that that instruction is atomic, right? So in that atomic instruction, you can say load the value, test it, and then set it to a 1. So all three can be done, and that way you have an atomic test and set instruction. Is that idea clear? Okay. So that is the minimum primitive that you need in a multiprocessor, in order to implement a multiprocessor, that you have a way by which you can ensure mutual exclusion. And once you have that, then you're good. So that is the test and set instruction. And so once I have test and set instruction, then I can implement the higher level primitive. So if I think about mutual exclusion lock, it says I want to get a lock, and basically what that, you know, the operating system now is using this test and set instruction in order to implement the mutual exclusion lock. And what it is doing is it is saying it is going to say that there is an integer x, and it is going to test and set the lock location, and if it got the lock, meaning the original value was 0, then we are good. We can return success. But because test and set, the atomic instruction, what is it going to do? It is going to return the old value and set the value to a 1. That is atomically being done by my new instruction in LC2200, right? So if x is equal to 0, then I know that originally the value was 0, and therefore I succeeded, right? And so I can return success to the thread that is calling it. Otherwise, if x is not 0, that means that somebody else got ahead of me and got the lock, and therefore I'm going to block the thread. Okay, is that idea clear? Right? So this is exactly what the operating system will do in terms of implementing a mutual exclusion lock. And for unlocking, it is pretty simple. You just set the lock value to 0. Right? Nick? No, go ahead. Well, so you're saying that you go and unlock L to be 0, right? That's what you're worried about. So somebody is calling unlock, and so what the operating system will do is the guy who has actually got the lock is the one that is trying to do the unlock. So in other words, you know, when so if I think about this is a data structure in the operating system, right? And similarly, in the operating system, you have a mutex lock. You have a data structure that is supported by the operating system called mutex lock, and so it is giving you this variable L, right? And so if a thread came along and locked it, okay, so it knows that T1 is the one that has the lock, right? And it may have a waiting queue of guys that are waiting for lock, so waiting for the lock, and so on, right? So if anybody tries to do an unlock, the operating system is going to check, is it the same thread that has the lock? Okay, if it isn't, it's going to simply deny that request, right? So the operating system is smart enough to check, to make sure that the unlock is being called by exactly the thread that gave the locking request. Shane? Pardon me? So, you know, there are different levels of implementation, right? So I'm saying what would be the right way to implement lock, okay? So I'm saying that that is the reason that you have to be very careful when you're dealing with threaded programs, that, you know, you have to look for so many things that can happen which you did not intend, right? Ideally, this is the semantics that you want the operating system to implement. So, well, you know, a good operating system will do it. The POSIX standards is actually asking for this kind of, so Shane is asking about POSIX standards. So there's something called the standards that people have come up with. IEEE is a standardization body, come up with a standardization for how threads semantics should be implemented. Just like, have ANSI C, right? C is a programming language, and there is a standard for that. And now different compilers may do different things, okay? So, but there is a semantic that is supposed to be established. Whether it is always followed or not, you have to be very worried about that, okay? But the standards are there to say that, make sure that it is adhered to, but we cannot guarantee that. So be aware of violations of the standards. Okay. Is that idea clear? So how this mutex lock works, and in the operating system, so you can implement it this way. And now the second thing that you want to do is, in terms of hardware support, you want support for locks, support for sharing, and support for page tables. So these are all the hardware support that you want. Okay. So let's talk about sharing. What I mean by sharing is, I want the threads to have, if I think about a process, the process is an address space, and independent threads should be seeing exactly the same copy of variables, right? Regardless of whether they are running on one processor or another processor. And this brings up the concept of a multiprocessor. Okay? So if you think about a multi-core single processor, or a box that contains multiple processors, they're all organized in this fashion, that you have a whole bunch of CPUs and you have shared memory, and there is a bus through which you get to the shared memory. Okay? So this is the organization, and so the system, meaning hardware plus the operating system, has to ensure three things. One is threads of the same processor share the same page table, right? Because they're all part of the same process, and therefore the page table is common for them. And they all have to have identical view of the memory. So a thread can be running here, a thread can be running here. They're all accessing memory. The copy of memory that they're going to see is going to be got to be the same. And threads have to have synchronization, atomicity. And we already saw that the third part we've taken care of right now, right? We have synchronization, atomicity for threads, because we've introduced a new instruction, the test and set instruction. Now, so let's look at the second one, threads having identical view of the memory. Why should that be a problem? Because there's shared memory here, there are threads running on these different processes. Why will they not have the same view of the memory? Why will they not have the same view of the memory? Is it a non-problem? The picture is flawed. Think about the slide that I showed you, not the slide, but the picture that I drew for you on Sunday, cache memory hierarchy, right? So between this guy and this guy, is there anything that sits in between? There are caches, several levels of caches sitting in between, right? And so when the caches are there, then the copy of memory is going to get into those caches. And the copy of memory that gets into this cache may be different from the copy that gets into this cache, and so on. And that is really the problem, that what you have is, the real picture is more like this, that you have a cache sitting in front of the CPU. And so when you access memory, you're first going to the cache. And only if you miss the cache, you're going to the memory, right? And so if each of these guys have independent decision making like this, then you have an issue. I can do a load x from here, a load x from here, and this guy can modify the local value of x that they've got, and others won't even know about it. Okay, and that's what is called the multiprocessor cache coherence problem. Okay, that you have multiple processors, each processor having its own cache, and when you have that, then one guy making modifications to their local copy in the cache, the others may not know about it. That's the multiprocessor cache coherence problem. What's the solution? Pardon me? Right policy meaning? Right. So you mean right through, not right back. Right through. So what Nick is suggesting is that reading is okay. They can have multiple copies. But anytime this guy wants to write to it, make sure that you write through to memory. Okay? Let's say I do that. How does it prevent this guy from still reading the old value? So what you want is, so far we've been thinking of the cache as a passive entity, right? It's passive in the sense that it's only reacting to what is coming from the CPU. If CPU says give me X, it gives it X, or if it doesn't have it, goes to memory and fetches it, right? But now we want to turn these caches into active entities, right? Not only is it serving the CPU, but it is also observing what is going on here, right? So if somebody is going to write to X, then this guy says, oh wait, somebody is trying to write to X and I have a copy of it, okay? And if I have a copy of it, I have one of two choices. What are the choices? Update it or delete it, right? I can either say, well, I'll get rid of it because somebody wrote to it, or I can update it. These are the two policies. I mean, you guys have gotten a PhD if you had done this 20 years back. So this is essentially the idea behind multiprocessor cache coherence and how to solve it. Okay. So the idea is when you have multiprocessors and you have caches, and what you want to do is when you have this value that is cached in multiple processors like this, when one of them tries to write to it, you can invalidate. So the first thing that I want to do when I want to modify X to X prime, I'm going to first send an invalidate. Okay, that's what Ron was saying, delete it, right? So first I'm going to tell everybody that I'm going to invalidate it. Here again, because each processor can be thinking simultaneously, multiple processors can at the same time say I want to write to it, right? But fortunately there is a shared resource called the bus. Only one guy can hold the bus at any point of time, right? So you can get a hold of the bus, and whoever gets a hold of the bus says invalidate X. Okay, as soon as you say invalidate X, everybody will invalidate the local copies. Okay, and once you invalidate it, Nick pointed out that, well, maybe you can write through. Now you have a choice. You don't have to write through, right? Now I can simply modify my local copy, and later on, and T2 may immediately say, I want to get a value, generates read access to X. What's going to happen then? It's going to be a cache fault, and it is going to go out here on the bus to get to memory. Is that a problem? It is a problem, but remember that all these guys are active, right? So this guy is watching the bus also and says, hey, this guy wants X, the value in memory is old, I've got the new value. So he can directly supply the value to the peer, right? So this is cache to cache transfer. So now you see that the caches become active entities where, when you want to modify something, you invalidate the old copies that may be existing in all the other peer caches, and then when somebody else wants it, then you supply it if you have the most up-to-date copy. That is one way of doing it. And the other way of doing it is to update it, and that is anytime I write to a location, I also send an update on the bus saying that X has changed to X prime. And everybody that happens to have a copy can locally update it. Okay? So these are two different solutions to the cache coherence problem, which is called write invalidate or write update. Okay? In the first case, it's invalidating upon a write. In the second case, it is updating upon a write. Okay? These are two different ways of approaching the same problem. And you guys came up with a solution. There are tons of papers written on how to do cache coherence, and you discovered it in 5 minutes. That's very good. Is that idea clear, how this multiprocessor cache coherence works? Yeah. Oh, so cache to cache transfer can be faster than getting it from memory, right? Right. No, so when you have multiprocessor cache hierarchy, things are a little bit more complicated, so we won't go there at this point, but I'm happy to talk about it offline. Okay? But the principle is the same. The principle is the same, that what you want to do is anytime you modify something, you want to notify it in the appropriate level in the memory hierarchy so that others can see it. Okay? And if you have a cache within a core, and that is and that is not visible to others, then you have to have some mechanism by which you can tell the others that you're changing something. Okay, so that is important to make sure that others can see that. And once you do that, then sharing is taken care of, right? So now all the data structures that is shared by a single the threads of a single process, they're all going to have a consistent view because of the fact that the hardware takes care of this. Is that idea clear? Okay. And what about page tables? So the third thing that I mentioned is page table. Is that a problem? That's not a problem because page table is in shared memory, and you know the cache coherence is that works for normal data works for page table entries also. They're all going to see the same page table entries. That's not a problem. But there is another side problem, and that is TLB. Okay, that is the translation look-aside buffer, which is also an entity that is inside the processor, just like a cache. It is inside the processor, and it is specific to each processor, and the operating system has to worry about the consistency of the TLB. Okay, because it's not something that the hardware takes care of. Hardware only takes care of the consistency of the caches. Okay, but the TLB consistency, the TLB, if there is a change in the TLB, that is something that has to be propagated by the operating system, and that's not a problem because you know when does the TLB change? TLB changes because of eviction of something from the TLB is not an issue. Okay, what is an issue is if the mapping that the operating system has established for a virtual page to a physical page, if that changes, then an old mapping can exist in some of the other caches, other TLBs, and that's the point at which the operating system has to say, you know, get rid of this particular TLB entry if you happen to have it in all the processors. Okay, so these are the ways in which you can actually make sure that your multi-threaded program can actually work in a multiprocessor. Okay, so these are the hardware side of dealing with it, and there are problems that that are in the book, and there are worked out problems in the book, not necessary for your test on Thursday, but make sure that you're familiar with those. And so if you don't mind, we can do a PRS for 5 minutes, which will be a warm up for your test. Okay, it's on caches. So the channel is D. All right, why don't we start with this one itself? So this is a repeat for those who came, at least some questions are repeat. All right. Okay, so that's very good. So 2 is the right answer, and some of 4 is okay, but not for getting a grade. Okay, so go to the next one. All right, very good. That's very good. That's very good. I think you guys are warmed up for the test for sure. Well, well, let's see. My goodness. So there's a direct map cache, right? And in a direct map cache, how many comparators do we need? You know what a comparator is, right? So if you look at this picture here, what is this picture? This is a picture of the direct map cache. So what you're doing is comparing, pulling a particular line and then comparing it against the high order bits, which means how many comparators do you need? Only one, right? And I'm surprised that quite a few of you have picked. I thought you warmed up. So the right answer is 4 here. Uh-huh. Was the question flawed? So the T-bit tag comparator for the entire cache. So the three bits are there that has to be compared, right? So you need T bits to be compared, but there's only one comparator that does that. Okay, so make sure. I mean, even if you didn't parse my sentence right, if you can't have the concept right, I'm fine with that. Okay, so that's that. So the right answer is 4. This is also a repeat for those who attended the Sunday. All right, so most of you have the right answer. That's very good. Right, so it's basically, you know that the average CPI of your pipeline processor gets affected by the amount of memory stalls that you have, right? So if you have 3% of cache misses per instruction and the miss penalty is 20, then 0.6 is the penalty that you pay. So it is 2.1 is the right answer. All right. And so long as you understand the concept, right? So okay, that's okay. Yeah. So let's stop here, and today you have Kirak again. Kirak is my graduate student. Doesn't have to come and do this, but he, out of the goodness of his heart, he's doing it. So give me a hand.